These are the notes for LT5 in the Newton's laws unit, and this target deals with Newton's third law of motion. And your task is to be able to identify the action and reaction forces from examples in everyday situations. You'll have to be able to identify those, and then as we go through here, you'll have to be able to kind of interpret what does that mean. All right, so identify action and reaction, that's the basis for what we do with this target. So to start off with, we're just going to get our third law definition. And the third law states, it's probably the most famous, the one you're most likely to remember from your middle school years. For every action, there is an equal and opposite reaction. Now, we're talking forces here, so don't take this to a more abstract level where, like, if I don't get my coffee in the morning, I am more tired, my reaction. Or if Michigan State loses, my reaction is rage, all right? That is not what we're talking about. None of the emotional, cognitive stuff here. We are talking forces. If you were in class, you would have watched a demo, but we've already probably done this. You take a balloon, blow it up, don't tie it off, but then let it go, and you know how the balloon makes that squeaky sound and goes flying around the room? Think about why that happens. So here's my attempt at drawing a balloon. And when that balloon, when we let it go, it's filled with air and let it go. We got to think about it. That air is flying out in all directions. Okay, it's going every which way. Yet if the air blows this way, we know the balloon doesn't follow it. And if it blows this way, the balloon doesn't go in the same direction. And it's all because of what's called an interaction. And we probably have a pretty good idea of what an interaction is. Think about an interaction between two people, right? There's oftentimes a pair. And I realize sometimes in normal non-physics life you could have an interaction of a group. But for physics, we worry about just a pair of forces. So a pair, hopefully we know in first two. Okay, so it's a pair of forces. And we label those forces the action force, and you can probably guess the reaction. Okay, the action and the reaction. So how you decide which is which does not matter. Okay, so there's no rule for naming them. There's kind of I don't know, just a common sense type thing, a logical thing, but you wouldn't be wrong if you flipped it. So here's what I mean. Let's say that the action is the balloon pushes out the air. Okay, the first thing we need to do is identify what are the two objects, the two things happening, the two forces. Well, we've got the balloon and we've got the air. Okay, air is a thing, so it counts as an object. The balloon pushes on the air. Kind of the common sense way we would flip this, then it sounds strange, I'm going to put it down here, is the air pushes on the balloon. And it's the air, so here's our two objects now. It is the air pushing on the balloon that actually moves it. Think back to the fan cart physics gizmo. The fans, if they're not on, that cart doesn't move. But when you turn a fan on, the fan is blowing the air out to the left, therefore the air pushes the cart to the right, right? So the fan blowing left pushes the cart to the right. It could be the same thing, let's say in outer space, space travel. And if we have space travel, we have a shuttle, and we'll look at this here in a second. We didn't think we could travel out there for a long time because, well, there's no air in space. But it doesn't matter. What if you have, so here, we'll throw this down. So that's space travel. Goodness knows this is getting to be a big deal, which is fantastic. But we're just going to call it a rocket for fun. A rocket pushes on fuel. All right, we've got some combustion going on. Rocket pushes on the gases. That does nothing in terms of moving the rocket through space. It's the reaction. So if this is our action, we could say the reaction is the gases push on the rocket. That's what moves it. And it took us a long time to figure out that that would work. And obviously we figured out that it does work. Alright, so all we do is flip stuff around. If you were in class, you'd get this sheet and we'd go through this together. The bat hits the ball. If they're going to call that the action force, then we would say our reaction force, you just flip it. The ball hits the bat. You know this. If you've ever fallen, you wiped out on a hard ground. The fact that you hit the ground is not what hurts. The ground hits you back. That's what hurts. All right, so a man pushes on the car pushes on the man. You can feel the resistance. The bus hits the bug. All right, well, the bug also hits the bus. But because of the second law, because this bus has a huge mass and the bug has a little baby mass, that's why the bug loses this fight. Okay, its body has to accelerate a lot more, and it can't, so it is a smudge on the window. Okay, so the athlete pushes on the ball pushes back. Foot on floor pushes back. Okay, all these things. It's pretty repetitive. It's the exact same thing. But there are a couple rules. I'm sorry, one more rule. We know there's no rule for naming. Next thing that is a little bit odd for us is that these forces do not cancel out. We are not calculating net force here, right? What we're looking at now is think about what these forces are pushing on. The gases are pushing on the rocket, okay? The rocket is the object in this one that's being pushed on. The rocket is pushing on gases. Those are different things. I know that sounds silly, but those are different objects. The balloon is pushing on the air here. And in the reaction, the air is pushing on the balloon. Those are different objects. If you were doing a free body diagram, you'd have to do one of the air. The air would have to be in a square, and the balloon would have to be in a square. Here, the gases would be in a square, and then the rocket would be in its own square. Okay, you don't lump them together. So they do not cancel out. Therefore, and the reason is because the forces act on different objects. So let's say we're talking about why can a person walking on a sidewalk. You might think, well, the action is the person pushes on the sidewalk. That's right, that makes sense. So the action is on the sidewalk. So the applied force, we could say, is on the sidewalk. The reaction, though, is the sidewalk pushes on the person. I probably should have said their feet, but it'll work. Different objects, they don't cancel out, you move along. There's this old comic strip, and if you Google, if you really want to see it, a horse cart comic in physics, there's this big long story about how a horse is hauling the farmer in his little cart, and the horse is a little too smart for his own good. He says, you know what, according to physics, I'm going to pull on the cart, and the cart is going to pull back, and we are not going to go anywhere, so this is a futile effort. And the farmer kind of scratches his head a little bit, and he says, you're right, but let's think about what actually does move a horse in a cart. And we could say, well, the action would be the horse's hooves on the ground. That's not what matters. That's just pushing on the ground. But assuming there's friction, those hooves are going to allow, the friction will allow the ground to push on the hooves. So the ground on the hooves of the horse, that is what moves a horse cart within the horse cart comic. All right, so if you see a question about that, it doesn't matter that you know it's a comic strip. Just why is anything able to move? Well, it's not your car tires pushing on the road that moves you. Because if you hit ice, you're still technically kind of pushing on the road. You're of a normal force, at least, in weight. But if that road can't push you back, if that ground can't push those hooves forward, the horse doesn't go anywhere. All right, so that is Newton's third law. Good luck.